Clinker Factor, the cement industry podcast.
Welcome to the Clinker Factor, a podcast from WCA, which looks at the cement industry's response to climate change around the world and other topics of interest. I'm Ian Riley, CEO of WCA, and your host on the Clinker Factor. The cement industry has used three levers traditionally to reduce both costs and CO2 emissions. Those three, of course, being energy efficiency, fuel switching, and reducing the clinker factor. Today, we look at two new technologies that are addressing the problems in more fundamental ways. So I'll be speaking to Gurinder Nagra, who's the founder of Furno, and Greg Houchins, the founder of Chement. Both of them are Breakthrough Energy Fellows, and Breakthrough Energy is the network founded by Bill Gates that aims to accelerate innovation and reduce greenhouse gas emissions. The program provides financial and professional resources to innovators working on early-stage climate technologies. Gurinder, let's start by asking you to give us a short background and introduction of how you got involved in this project.
Sure. Thanks, Ian. Thanks for having me. Yeah, so my involvement in the project really began from a class at Stanford, initially as a side project. I was doing my PhD at Stanford, primarily working on carbon capture and storage. Kind of realized, in order to actually build a company, I didn't really think that was going to be economically viable in and of itself. Started looking at tangential industries that overlapped with my background with geochemistry, and cement was one of these high impact, overlooked sectors that I quickly dove into, and over the course of 2 years explored three different technologies and eventually landed on the insights behind Furno.
Okay, well that sounds a very rational approach. And what made you select Furno out of those that you looked at?
The whole process of the class is you do a lot of customer discovery. You generally use some kind of a technology to do a deep dive into the market. You build out techno-economic analyses, and by the third time I took the class, I was kind of like, okay, a lot of the technologies that had been in the space to date had very much started out of a lab and were trying to push a technology out into the market. And so the third time around, I was like, well, why don't we start with a business problem and work our way back? And that seemed to stick with customers in terms of an actual problem. And then, it kind of just continued on from there.
So what was the business problem that you identified?
So there was two. So one of them is primarily around this mismatch between supply and demand. So the way that we've been building cement plants to date over the last 50 years is they've been getting bigger and bigger and bigger, and they're very much consolidated towards high density, high volume regions within a 150 mile radius, and it takes you 5 years to build one of these things. You break even in 12 years plus, and that's okay to date, but then over the next 20-30 years, the majority of demand is going to be coming from high growth regions where assets are not currently. So then the big question is, okay, how do we get assets to where they need to be in order to provide cement for where demand is going over the next 20-30 years? So that was one of the major challenges that I saw. And then at the same time, where there are assets, there's huge regulatory constraints around CO2 emissions and just air quality emissions. And so it's like, how are those existing assets going to adapt to those regulatory environments? So they're kind of getting choked with these two key challenges that are coming around the corner.
So you segmented that really into sort of two groups. So the high growth areas are mainly Africa and India, where they're going to need a lot more capacity. And then the developed world where there's plenty of capacity, but it's generating CO2 emissions in an environment where that's going to become increasingly costly. Is that kind of the right way to see it?
Yeah. And so our whole thinking was, well, what is the ideal technology that can fit and solution that can fit into solving both of those two key challenges that are coming around the corner? And so our whole thing was, well, what if we build smaller scale, standardized modular plants that can enter and exit markets quickly and efficiently, and they can actually adapt to these changing regulatory environments that are coming around the corner? And then it was like, okay, why haven't people done this to date? And then that opened up a new can of worms, and that's where the journey began.
Of course, people have looked at modular plants before, but you can see around the world there are very few modular plants. There are some grinding stations that have been done on a modular basis, but integrated plants, you don't really see that. So it's not that people haven't thought about it, they haven't been able to make it work. So what is it that you think, that your insight that would enable these plants to actually work?
Yeah, so we've developed a new type of plant or reactor that essentially combines all 4 stages of cement production into one single step reactor. And so this is like a 2-meter high, 1.5-meter type unit, does preheating, calcining, sintering, cooling. And so you can imagine, like, well, what if you could build, integrated plants. So the key kind of bottleneck of getting to that small scale is the kiln and the whole heating and cooling process, right? If you can get that small, grinders, raw mills, you can get at a much smaller scale. Like, what if you could put that thing in a shipping container? All of a sudden, you've got like this standardized unit where your asset's not suddenly at risk because demand is fluctuating in a particular region.
So how small are we talking about in terms of capacity? What is one unit going to produce?
I mean, at the moment, we're thinking like the first commercial unit will be about a 20-ton a day like module. And then, if you want to hit 100, 200-ton a day capacity for a plant, you just copy paste. And so that allows you to actually leverage a learning curve, especially if you have a standardized design. One module could be made of multiple modules where you can take a segment out, do repairs, kind of like fixing a spare tire on a car. Spare tire on a car.
Yeah. So, I mean, some people might say that's sort of going back 100 years or maybe a bit more than 100 years to the scale of plant that we had many years ago. And I suppose in a sense that is the concept that you have. So how does that smaller scale help you? I mean, because obviously there's some economies of scale in building plants generally. You can realize some of those economies by having standard modules, but how do you make it work from the standpoint of just the cost efficiency?
Yeah, so let's kind of break down, I guess, the key costs. If you have, let's say, raw materials are one of your costs, right? If you have 100 or 200 ton a day plant and you have like 1,000 ton a day plant, the raw material costs may vary a little. They will be slightly higher for the 100 ton a day plant, but not that much. If you have our technology is more energy efficient, so it's probably around 2 to 2.5 gigajoules per ton of cement, even at that scale. So that's a reduction in your energy requirement. And then maintenance, ideally, with these standardized units, over time, you're able to bring that down because you have predictability with maintenance, whereas traditional plants, they're very customized. So you can also, I guess, make the assumption that the maintenance costs will go down over time. And the key thing that's left over is labor. We want to build these things such that they're automated end to end, and you can control them remotely from let's say we're in San Francisco, we have a central control station, and then you have 200 modules operating all around the US. If one is down, you can take one out, put another one in. Maybe you send one person there once a month to do annual checkup or maintenance, but you shouldn't need someone in terms of the operation of the plant actually there. The other thing is, it opens up different types of business models. Like some of these, concrete producers actually own their own limestone quarries, so they can do the mining and the transport and start feeding the material, and we just operate and run these units remotely. Cuts all our labor costs.
Yeah. So energy costs, of course, are the biggest cost in producing cement, and so if you can be more efficient, that makes sense. The industry and the engineering suppliers to the industry have spent many man years and effort trying to improve efficiency, and we have 6 and even 7 stage preheater towers and new designs of calciner and so forth. And that's getting to maybe 2.7 gigajoules as sort of the best that we're seeing. How are you able to improve on that? What's the sort of breakthrough in terms of energy efficiency?
Yeah, so it really goes back down to heat transfer, our combustion system. We've developed a new type of combustion system and a reactor design that enables much higher heat transfer. So there's a lot less heat lost. If you go to a cement plant, you stand 40 foot away, you're going to feel the heat from the unit. Whereas with our unit, you can touch the surface of the outside of the actual unit. There's a lot less opportunity for heat to actually be lost. One of the kind of leverage, I guess, levers for heat transfer is surface area to material contact or energy to material contact. If you look at the inside of a rotary kiln, there's actually not very much material in there. You actually have to heat up the whole kiln in order to actually get the material up to that temperature. And the whole point of a preheater, a precalciner, and a cooler cooler is to actually make up for the inefficiency of the kiln itself. So the industry is going down this route of adding on capital cost, adding on capital inefficiency to make up for an inefficient system that's really optimized around scale, not efficiency.
Okay, so it's really around just the heat loss and therefore the efficiency that you work on. So even with the new design, is it really more economical to do it at such a small scale? Would it not be more economical to have, I don't know, 1,000 tons a day or 5,000 tons a day with that new design?
So traditionally, to pull off those type of projects, they are custom built. And so every time you do custom construction of these large plants, you have to pay for the installation, the design and engineering, all of these layers of contractors to pull this type of a project off. And it just kind of balloons your capital cost. We really want to leverage the learning curve in terms of the capital cost reduction. That's why we're keeping it small. And it also allows you to remain more agile. Yeah, like in terms of the operating costs, we think we can be competitive at that small of a scale. And that's actually an advantage long-term in terms of adaptability.
I'm just thinking about the numbers here. So 20 tons a day is going to be what, 7,000 tons a year, right? So if we were thinking about India, which might add, I don't know, 200 million tons a year of capacity in the next 10 years, I mean, that's really a lot of units, that sort of scale.
Yeah, so I mean, this is version 1. So a 20 ton a day unit may be used for, 100 ton a day, 200 ton a day plant at a time. I guess 80 years ago, India did have a lot of, smaller scale called vertical shaft kilns. That system worked. It's just those were more inefficient because they were using like coal as a fuel. Yeah, the energy efficiency was not competitive with rotary kilns. And then also the government actually subsidized transport to incentivize rotary kilns, which took away the major advantage of those vertical shaft kilns. We initially will start off with these 100 ton a day, 200 ton a day plants or these opportunities or gaps in the market. And then, there's no reason why you can't scale up to a 50 ton a day or 100 ton a day unit. But this is just going to make us quicker for us to actually get to market rather than having to take that traditional route of technology development, which takes 15 years.
So do you have a target for the cost per ton of capacity that you're aiming for?
Yeah, so it's around $200 to $250 a ton.
So I think in India at the moment that would be more expensive, right, than the traditional plants that are being built.
200 to 250 in developed economies.
In developed economies, yeah. I think that would be roughly what people are spending, maybe a little bit less. I mean, I think probably 200 to 300 is probably the range. There are plenty of examples over that as well. I think probably in India it's closer to 100 to 150 as a range at the moment, yeah.
We found it's about half of the developed world. I mean, a lot of the data points that we've had on the developed world, we're seeing capital cost estimates of plants being around $400 to $500 a ton rather than what's quoted.
There are certainly examples of that. I think if we look at who's building plants these days, I mean, the Chinese companies building plants outside China are probably spending $100 to $150, which is similar to the Indian level. So I think for new plants then, because the majority of new plants are going to be in the developing world, not the developed world. So that's probably the going rate. But as you say, they are much more expensive in the developed world. But so suppose we can get on to the second part of what you were talking about in terms of the reduction in CO2 emissions, because this will be the attraction of the plants in developed countries. Yeah? So what are you doing to eliminate or reduce the CO2 emissions?
Yeah, so I mean, one of the, I guess, core advantages is that our system is completely gas-based, so it's fuel flexible. We can completely use natural gas or methane as a fuel. We can use biogas, we can use syngas, we can use hydrogen. It's fuel agnostic. So if you compare that with coal today, gas emits half the amount of CO2 per gigajoule of energy as coal does. So that cuts your fuel emissions. And then since it's a more efficient process in terms of gigajoules per ton, it can actually reduce emissions even further. So we're thinking about a 35% emissions reduction versus traditional cement plant technology. The other advantage is so that's without doing any carbon capture and storage. It's much more easier for us to adapt to oxy-combustion, so we can use oxygen and CO2 or a synthetic air to produce a pure stream of CO2 from one single point in the actual reactor. And traditional plants, it's really expensive to do that separation process because not only do you have to separate out the nitrogen, but you also have to take into account all of the impurities in the fuel that you have to scrub out particulate matter and the trace elements. And so that just adds cost onto your separation unit. Gas is a much more clean burning fuel, and so it does not have that challenge.
So a lot of people are trying to change from using coal to using biogenic sources of fuel. Yeah, so they have biogenic CO2, which obviously is counted differently. Do you anticipate that you'll be able to use alternative fuels in your technology?
As far as my knowledge, alternative fuels are like plastic tires or rubber tires.
So you get alternative fuels that are waste-based. So exactly that, the rubber tires or plastics and wood and paper and so forth from various waste streams. Also biomass. So I don't know, rice husks and wood chips and this kind of thing, where the CO2 is biogenic and therefore is counted differently in terms of emission.
Yeah, so those are solid-based fuels. So ours is completely gas-based. So we would not use those. To
get back to the economics, then if you're talking about a 7,000-ton plant, $200, so you're talking about sort of $1.5 million for a module, are you? Is that the way it would work?
Yeah.
Okay. Oh, it sounds very interesting. Now, how close are you to getting one of these to deployment?
So we've proven our tech at like a benchtop type scale. We're currently built out an R&D pilot reactor that's large enough to produce samples customers. So we should be producing samples early to mid next year, just ordinary Portland cement. So that's going to be partly to sending samples, partly understanding the operating parameters of our system, understanding the window of operation. And then the next stage after that will be commercial demo unit, which will be that 10, 20 ton a day unit, which we just copy paste.
And so you're hoping to get there, what, in 2-3 years or?
Yeah, about that.
Okay, so still a bit of development work to do there, but interesting space to watch. So what do you see as being the major hurdles that you'll have to overcome in the next 3 years to realize this?
I think it's mainly one of the advantages that traditional plants have is that you've separated out all of these 4 stages of production, so you can dial each one separately and optimize it. So that makes their process controls. There's less complexity they have to deal with. With ours, since it's all compressed into one single step reactor, you have to understand all of the sensitivities of the system and the operating parameters. Okay, if you turn this dial, how does that influence the whole system? So really developing that operating window is what we're really going to be focusing on over the next year. And so that there's no way around that but just testing and iteration and learning.
And is there a role for AI in helping you with plant control?
Yes, there is. So this is one of the other angles, I guess, or advantages of our system is that, so traditional plants, time is not really a variable, right? Because they're optimized for throughput and producing as much cement as possible throughout your plant. So the only dial you're really able to turn is energy. So if your cement or burnability of let's say you have too much free lime in your cement after you've run your raw material through your plant, the only dial you can turn is increasing the heat to make sure your cement hits spec. So you may be overheating the material and it's a more inefficient process than what's actually required to hit spec. We're able to actually control time and temperature to optimize the operating parameters that are required to actually make cement in the most efficient, precise way possible. And so over time, we can develop models that can use one standardized plant design, irrespective of the location where you are, where you can relate the raw material profile to the final clinker quality that you want. So it can be a fully automated process where you don't really need a person to say, oh, I need to crank up the heat here in order to get the cement that I want. And then, you have knock-on effects from that, like you burn a hole in your kiln. And
well, it's not the only choice you got, though. I mean, you could also slow down the feed rate or adjust the raw meal.
You could, but then that would cost you. And then maybe you're not able to completely, hit your utilization rate of your plant.
In many countries, that's not really a problem. Of course, in the US at the moment, you've got quite a lot of imports. So in the US, they're very keen on optimizing the plants. but in many countries, there's a lot of excess capacity. So there isn't the same sort of pressure to get the last ton out of plants as there perhaps used to be. Building out that operating system is part of it. What are the other key challenges that you see yourself facing in the next 2 or 3 years?
I mean, one of the other things is finding people in the cement space, getting people interested in the cement space. The industry is kind of, I don't want to say an aging industry, but like the expertise is very, very niche. And so kind of bringing that back to a new generation instead of starting from scratch is always I think a challenge.
Yeah, no, I think you're right that the demands traditionally have been fairly straightforward for the majority of the employees. But one of the things that I think the industry is facing as a challenge, but is also kind of an exciting challenge, is because of the pressures of responding to climate change, and there's a lot of new ideas and new technologies that the industry is looking at. It is starting to attract more innovative people into the industry. So the technology that you have here is an example of the sort of both the challenge and the opportunity that the industry will have in the next few years. Are there any other technologies that you've seen as a result of being in this space and your involvement with breakthrough energy that excite you or you'd like to highlight?
Sure. So I spent about two years just exploring a bunch of different technologies in the space prior to landing on Furno. And one of the things that I kind of saw was that a lot of these technologies start out in a lab and they tend to address one segment of a larger system, which is ultimately designed to almost like cannibalize that innovation. So I think you really need to address that whole system in order to really bring innovation into the forefront. So, one of the advantages or the whole reason why we're going for these module and smaller scale plants is that we want to build a new type of company that designs, builds, and operates these plants. So that allows you to really align incentives and unlock innovation in the sector, because you don't need to build custom big plants in order to stay in business or win on cost.
Traditionally, I think cement companies have started by finding a suitable limestone, that's close to the market they want to serve. So if you're talking, but that's kind of a local, expertise, isn't it? Because anytime you're dealing with land and you tend to be dealing with a lot of residents and landowners, I mean, all of this is messy and very local in terms of the connections and expertise you need to deal with that. So is that something that you would see yourself getting involved, or is that will be a partner that deals with that side of things?
I mean, early on, it will be a partner. So, one potential business model is this smaller scale plants open up different types of business models, which is, plants as a service. So like a lot of these independent concrete producers actually own limestone quarries, which are too small and to basically justify constructing a huge cement plant on those sites. So this kind of enables them to vertically integrate a consistent, reliable supply of cement instead of having to source cement from multiple different suppliers.
No, that would certainly be a disruption of the current supply chain. So, Gurinder, it's been a pleasure speaking to you today, and I wish you all the very best with your development work. It sounds as if you've got a busy 3 years ahead of you.
Yeah, thanks so much for having me, Ian.
It's a pleasure. My second guest today is Greg Houchins, who's founder of Chement and is developing an electrochemical process to replace the normal thermal process that we use to make cement. So, Greg, welcome. Can you start with an introduction of your background and how you came to found Chement?
Thanks a lot for having me here. I'm really excited to be on the podcast. So my background is in physics, actually. I did my PhD in physics working mostly on lithium-ion batteries. So I come from an electrochemistry background and just kind of stumbled into cement working on my PhD in 2018 and was just taken aback by the scale of the problem, the amount of CO2 emission in it, despite it being such a common material. And as I thought about the problem more, I realized that there's a lot of similar chemistry systems in the way that cement is made and then also the way that chemistry with it works. Merely just swapping the calcium for the lithium. As I finished up my PhD, I couldn't help but to think of the problem and actually come up with the technology that I'm working on at Chement and through the Breakthrough Energy Fellows Program.
So as I understand, Chement is trying to use the same raw materials as a traditional cement process to make an identical product to Portland cement. Is that right?
Yeah, that's exactly correct. Yeah. So reimagine the process, but kind of keep the final product the same. And the idea is that we can now use alternative electricity, renewable electricity, as the goal instead of conventionally fossil fuels, and immediately reduce the emissions just from the energy.
So can you explain how you do that? So what you're talking about is eliminating the emissions that would normally be from the fuel by substituting renewable electricity. How do you do that?
Yeah, that's correct. So I guess really just to talk about the way that conventional cement is made, it's now done in a two-step process. So you take a source of calcium, which is usually limestone, and then you calcine it to release the CO2, and now you have calcium oxide, which is then ready to react with a source of silica to make calcium silicates, which are the predominant material in cement. So in Chement's technology, we attempt to do those two processes with electricity. So we apply a potential to take the calcium out of that limestone and then stick it inside of the silica. And essentially, this is looking like the same way you would charge a battery, where in batteries, you take lithium out of one material and stick it in the other, and you drive that reaction with an applied potential rather than heat. So our process is working at room temperature versus the really high temperatures of a conventional cement kiln, but we're getting that kind of activation energy for the reaction with the voltage.
So I think using that battery metaphor, we can understand the sort of principle of how it's supposed to work. But I mean, in practice, how do you feed raw material in? Is it going to be a batch process, or is it possible to make it continuous?
Yeah, so the ultimate goal is to make it continuous. So we are early in our development working in a batch process now to really understand the process, but eventually we do want to get it to a continuous process. And that is kind of one of the challenges that we're currently facing, is thinking about how we take, this metaphor of batteries, which are conventionally very batch, it's inside this closed cell, and open up the system so that we can continually feed the raw materials in as conventional cement is done. We're just feeding the raw materials in and constantly getting the product out.
And are there existing industrial processes that are similar enough that you can learn from them?
Yeah, that's a great thing. Great question, because there are not a lot of large-scale electrochemical processes. But one really great example that I like to think about is primary aluminum production. And in that process, you have a constant feed of aluminum oxide into a giant pot. And in that pot, you use electricity to precipitate out pure aluminum, and you have some counter reaction for what the oxygen does. And that is actually a semi-batch process, because while the aluminum oxide is continuously flowing in, you have to every once in a while suck out the aluminum, and then additionally the anodes, which are coke anodes, have to be replaced every once in a while. So that's one process we're looking at to try to model our development after, is if we can't go straight to continuous process, can we just make a semi-batch process where maybe we have a continuous source of calcium, and then every once in a while we have to harvest calcium silicates, just like you do in aluminum production. And then maybe that will evolve to a way that we can continuously do both.
So if we think about the scale at which we need to deploy decarbonization technologies, then one of the things that limits the speed of deployment is the cost of the technology. So we can see that what the cement industry has done so far is largely steps that can be taken to reduce costs and reduce CO2 at the same time, and that we're just starting to see now in some of the jurisdictions with higher effective carbon pricing that we start to go a bit beyond that. So when you look at the process, what is the expectation that you have in terms of possible costs? Is it going to be something that you think is competitive with a traditional process, or competitive when you take into account the carbon cost saved?
Yeah, so since the major thing we're doing is replacing the energy, going from coal or other thermal fuels to electricity, energy does dominate the cost competitiveness. So basically the cost of electricity really changes how competitive this is. And I think just the actual cost of electricity that you can get, especially for renewable electricity, is always changing. But I think if we go to, I guess, 2 or 3 cents per kilowatt hour with this process, we get to cost competitive, ignoring a cost of carbon. And actually, I think hopefully, if you look at some of the power purchase agreements for renewable electricity that are being developed in, especially in the United States today, I guess 2 to 3 cents per kilowatt hour is actually right in the ballpark of what this electricity is being sold for. So I don't think we're far off from that. And if that price can continually drive down, maybe even 1 cent per kilowatt hour, I think this becomes more competitive. And something that bolsters that cost competitiveness of the energy price would be that this process is actually more energy efficient. So this is coming from the fact that we're doing a lower temperature process versus a high temperature process. We're not losing energy to heat. We're able to really have a high efficiency of the energy that goes in is going towards the chemical reaction. And therefore, the total energy required is lower, and then your energy cost can decrease.
And do you have a time frame for getting from where you are today to something that's producing not perhaps commercial quantities, but at least a sort of pilot scale quantity?
Yeah, the question of pilot is something that we're thinking about a lot, especially even the question of like, what is a pilot scale? Like what is a good scale to demonstrate this in a more realistic setting? Like I talked about, where we're using real world materials, or we're to introduce some of that flexibility, or maybe even just test that flexibility. And I think the timeline we're kind of working on is, can we maybe in the next year or two just design that pilot scale, or understand what that needs to be, and start to think about what kind of partners we're going to need to develop that. Ideally we would want some land to put it on, maybe next to a quarry, maybe next to a current cement line. How big is it going to be? How much is it going to cost? And kind of what are the things that we really want to demonstrate? And I think kind of to get to that point, to really feel confident about going to the next step of a pilot, which will probably be close to tons, or ideally many kilograms. I think we're trying to get in the lab up to the kilogram scale in the lab, which is a bit of a jump already, but it's something I think we can accomplish.
Okay, well, thanks for that. And Greg, I think it's a very interesting technology that you have there. I wish you every success and speed with that. So thank you for talking to me today.